We're going to be looking at a quick recap of our exothermic and endothermic reactions from the previous video. So last time we looked at the difference between exothermic and endothermic reactions. Exothermic, that X being like exit, so our thermal energy is being released from the reaction, whereas in our endothermic, our energy is being taken in by the reaction. In both cases, it's our thermal energy, what we often think of as heat. So energy released to the surroundings, we end up with an increase in temperature. An example that we looked at last lesson was combustion reactions such as burning a candle. We also talked about things such as hand warmers, where they're again releasing energy to the surroundings and causing an increase in temperature. Our endothermic reactions, we've said energy is taken in from the surroundings that causes a decrease in temperature, and an example of that we looked at was melting ice. We talked a bit about what activation energy was. So when we're burning methane gas, for example, lighting a Bunsen burner, that reaction going on there is your methane reacting with oxygen in the air. It's a combustion reaction, and therefore it's an example of an exothermic reaction. But in order to light our Bunsen burner, we always use a splint or a match, and this is because we need something to kick off this reaction. We need some energy to put in order to start this reaction off, and that's our activation energy. And so that was the minimum energy we need in order for our reaction to actually begin. We showed that in our reaction profiles as the hill that we need to overcome in order to then go down to the products. So here we can see our reactants on the left hand side, products on the right hand side, and our activation energy is that energy required to go up the hill before going down to the products. In both exothermic and endothermic reactions, there is an activation energy that must be overcome in order to make those products. So we can also look at the temperature changes of these reactions. So exothermic reactions, we've already said, as the reaction happens, we're increasing the temperature. So here going from 25 to 45 degrees. But once that reaction's finished, it will then cool back down to the regular room temperature of about 25 degrees. With endothermic reactions, we're taking in energy, and so we have a temperature decrease. So here going from 25 degrees down to 5 degrees as that energy is taken in. And then as the reaction finishes, then the temperature will balance back out to room temperature of about 25 degrees Celsius. Okay, so we looked at how our exothermic reactions release energy to the surroundings, causing an increase in temperature, whereas our endothermic reactions, we are taking in energy from the surroundings and therefore causing a decrease in temperature. But what we want to think about for this is where that energy is actually coming from. And here we have differences between our reactants and products energy. But here we're talking about chemical energy. So when we were talking about our exothermic and endothermic reactions, we were talking about thermal energy being released to the surroundings and thermal energy taken in from the surroundings. But our reactants and products, they are both stores of chemical energy. And this chemical energy is stored in the bonds of the molecules of our products and reactants. And we end up with an exothermic reaction when the chemical store of products is less than the chemical store of the reactants, and it's exothermic, whereas when our chemical store of the products is greater than our reactants, we end up with an endothermic reaction. And so when our energy is being released to the surroundings, our energy is coming from our chemical store of our reactants and being transferred to the thermal store of the surroundings. Similarly, with our endothermic, our energy is being given to our chemical store of our products, as that chemical store of the products is greater than the chemical store of the reactants. We need to take in that energy from the thermal store of the surroundings into the chemical store of the products. When we do bond energy calculations, we consider the energies of our bonds, and our bond energies are measured in kilojoules per mole. So it's the amount of energy per a mole of those bonds. So we've looked at moles before. It's that Avogadro's constant, 6.02 times 10 to the 23. That's the number of bonds in which they're referring to when we're talking about the energy associated with them. So when we're then calculating our energy release, our energy taken in, our energy changes effectively, they will also be given in those kilojoule per mole unit. And the way in which we need to think about those is what's happening to our reactants and our products in order for a reaction to happen. So we're going to look at an example of the combustion of methane, which we know is an exothermic reaction as it is a combustion reaction. So we're going to be looking at releasing energy to the surroundings, and in this reaction we are reacting methane and oxygen to form carbon dioxide if it's complete combustion, and water. So thinking about what's happening to our molecules, well, we've got carbon attached to 4 hydrogens in methane, which is CH4, and we've got oxygen atoms. These have double covalent bonds, and we've got carbon dioxide, again double covalent bonds to those oxygens, and we have water molecules that are produced. So first thing we need to do is make sure it's balanced. Carbons, we've got 1 on the left hand side, 1 on the right hand side. Happy with those. Hydrogens, we've got 1, 2, 3, 4 on the left hand side, but only 2 on the right hand side. So we need to increase our numbers of hydrogens on the right hand side by adding another water molecule. So now looking at our number of oxygens, we've got 2 on the left hand side, but on our right hand side we've got 1, 2, 3, 4 oxygen atoms. So we're going to need to increase our number of oxygens on our left hand side, so adding another of those 2 oxygen atoms as an oxygen molecule, and we get our balanced equation CH4 plus 2O2 goes to CO2 plus 2H2O. However, actually drawing it out with our ball and stick model, that's showing us our bonds in which we are changing during this reaction. So in order for this reaction to happen, thinking about what chemical reactions actually are, we're rearranging the atoms and how they're connected to each other in order to form different molecules. So our carbon and hydrogen bonds are going to have to break. Our oxygen and oxygen bonds are going to have to break. Our carbon and oxygen bonds on this side, however, they're what's needing to be formed. Similarly, our oxygen and hydrogen bonds, they also need to be formed. So when we're talking about reactions, what we're talking about is bonds breaking of our reactants and bonds forming in our products. In order to break bonds, we're going to have to put energy in, as that's what causes that upwards part of our reaction profile, is that we need to have to break those reactants bonds. Going down the slope of the reaction profile though, we're going to be releasing energy. So when we are breaking bonds, we are taking in energy from the surroundings, and so breaking bonds is an endothermic process, and our forming bonds, we release energy as we go down the slope, and so that is an exothermic process. So formation of bonds is an exothermic process, whereas our breaking bonds, that is an endothermic process. And in order to start our reaction, so we looked earlier about our activation energy, it's our activation energy that helps with this endothermic process of breaking bonds. So our activation energy is needed to start the bond breaking. So looking at our methane example, we had CH4 plus 2 oxygens, and we were forming CO2 and 2 water molecules. So looking at what bonds we were forming, we were forming 1, 2 C double bond O's and 1, 2, 3, 4 of our OH bonds, whereas our breaking bonds, we were having 1, 2, 3, 4 of our CHs and 2 of our O double bond O's. So in all of our questions we end up being given the data for our different bond energies. So reading on the table that was in the question, so our bond energy for CH is 414 kilojoules per mole, and our O2 is 498, and our CO is 803, and our OH is 464 kilojoules per mole. But as we have multiples of these bonds, we need to be timesing them by the number of each bonds that we have. So timesing our CH by 4, our OO by 2, our CO by 2, and our OH by 4. So we can then calculate our energy of bonds breaking by doing our 4 times 414 plus our 2 times 498 and our energy of bonds forming, we're going to do 2 times 803 plus 4 times 464, and so we will need to put those all into a calculator. And so our top one comes out to be 2652 kilojoules per mole. Is our energy of bonds breaking, and our energy of bonds forming is 3462 kilojoules per mole. So thinking about that enthalpy diagram, we're going up as we're breaking bonds, down as we're forming bonds. So forming bonds is our exothermic and is negative, whereas our breaking bonds, we're taking in energy, it's going up, it's positive. So we can use that to then be able to calculate this energy change between our reactants and our products. So we can treat them like vectors, if you've done those in maths, where your resultant vector is the sum of the two. So those two arrows together and you then end up with your resultant being the sum of those two arrows. However, if you haven't done vectors, that's obviously going to be quite confusing. But what you can do is looking at the arrows, or by putting the signs into place. So plus 2652 and minus 3462. So we're adding 2652 and then we're subtracting 3462. So plus 2652 minus 3462, and that gives us minus 810 kilojoules per mole. And here we've got that negative sign showing us that it is an exothermic process or reaction. And what we're doing here is it's our bonds breaking minus our bonds forming. As this minus sign is due to it being exothermic, it's due to it being negative, and so we include it there.